Okay, in this video we're going to discuss the interior angles of a polygon. Interior means inside. Polygon, well, poly is Greek for many. You can think about Polynesia. You could think about polyamory or polygamy or polynomial. Poly just means many or multiple. Gon means corner or angle. People think it might come from the Greek word for knees. You think about something that has many knees or many joints. Any shape with multiple sides is a polygon. So we're going to look at triangles, quadrilaterals, squares, rectangles, pentagons, hexagons, decagons, whatever. They're all polygons. But we'll start with the simplest one, the triangles, only three sides. You probably know that all three interior angles of any triangle, whether it's a right triangle, an acute triangle, an obtuse triangle, sum to 180 degrees. So 65 and 75 is 140 degrees. So to get up to 180, C must be 40. Quick way to do that kind of procedurally is if I start with 180 and I subtract all the other angles, whatever left over must be angle C. So 180 minus 65 minus 75 will be 40 degrees. If I want to explain why I know that, I could say C equals 40 degrees, and in brackets I could say by IATT. So often in this unit, when we know something, it's nice to know, well, how did you know that result? We call this the interior angles of a triangle theorem. So IATT, interior angles of a triangle theorem. Or you could just even write in a sentence, because all the angles sum to 180. But it's nice to have some short forms. Why do we call them theorems in math and not theory? So Pythagorean theorem, we're going to learn some angle theorems. Well, in math, we can actually prove something. So we're logically positive that it's the case. So we call it a theorem. In science, you more often hear that word theory, the theory of evolution. Because in science, we don't necessarily prove things from kind of a logical start, but we prove things using the scientific method or evidence. And so a theory is something that the evidence supports and it hasn't yet been disproved. But in math, a theorem is something that has been proved from logic or from axioms, and it would be impossible to disprove. Anyway, so there's the remaining angle triangle. Another tip for communication is we're usually going to use capital English letters or capital Greek letters to represent angles. So I have capital A, B, C on this triangle. Okay, let's move from three-sided shapes to four-sided shapes. I've got two quadrilaterals here. On the left, I have a regular quadrilateral. Regular just means all the angles and all the side lengths are the same. So a regular quadrilateral, we've got a special name for it. It's called a square. You probably know a square has four 90-degree angles. So the interior angles of a square add up to 360. 90 times 4. And that's actually true for any quadrilateral. This is an irregular quadrilateral. It's not a trapezoid. It's not a parallelogram. It's not a rhombus. I don't know. We could estimate that one looks like a very large obtuse angle, maybe 160 degrees. Maybe that one's 60 degrees, and maybe that's 90. So we know that if I, again, label these, maybe P, Q, R, S, that all of them add up to 360. And if I know three of them, then R must be what's left over. So I could do 360 minus 90 minus 60 minus 160. And so R is 50 degrees. So again, if we know that the interior angles of a polygon add to some constant, and quadrilaterals always add to 360, then I can always just find a missing angle by subtracting. Okay, let's keep going. We got triangles, quadrilaterals. The next one is a pentagon, and the interior angles of a pentagon, any pentagon, are going to add up to 540 degrees. So if I've got quadrilaterals, triangles, and now we've done pentagons. So a triangle is three sides, and the interior angles sum to 180. Quadrilaterals are four, they sum to 360. It's hard to tell a pattern just from these two. Like, is it doubling each time? Is it adding 180? Well, it turns out the latter is true. So pentagon has five sides, five angles, and they sum to 540 degrees. You can probably guess now, if we follow the pattern, it's just a linear relationship, right? It's got a slope, you could say, of 180, or a rate of change of 180 degrees each time I increase the number of sides of the shape. So a hexagon is going to sum to 720. So To find a pattern, we're starting with 180 for the triangle. So the pattern is n minus 2 times 180 is going to represent the sum of the interior angles for any polygon, where n is the number of sides. So we can test that for a hexagon. It would be 180 n minus 2. For a hexagon, I could plug in 6 for n. Just following BEDMAS, I'll resolve my brackets, and then 180 times n. Sure enough, a hexagon is 720. And that's going to work for any polygon. If I've got a decagon is 10 sides. What do the interior angles sum to? Well, it would be 180 times 10 minus 2, which equals 180 times 8. So the interior angles of a decagon must add to 1440 degrees. The only other thing to know about interior angles is that if the polygon is regular, all the angles are equal. So for example, a square is regular, an equilateral triangle is regular, a pentagon where all the sides are the same. I'm not sure if this is quite regular. If I want to find out any one of those interior angles, I could just take the total and then divide by the number of angles. So for example, our formula for any interior angle is going to be 180 n minus 2. That's the total. And then I could divide by n to find out how much is each of these interior angles. So in this pentagon, for example, I would have 180 times 5 minus 2 divided by 5, which will be 180 times 3 divided by 5, 540 divided by 5. And so that's going to be 108 degrees. The more sides I have, the larger these interior angles are going to get. So in an equilateral triangle, 180 divided by 3, they're each 60. In a square, we know they're each 90. In a regular pentagon, they're each 108. You notice that the angle's got to be larger so I can fit more sides around the edge. For our decagon, well, there are 10 of those angles, so I could divide by 10. So each angle in a decagon is 144 degrees. That's a big obtuse angle because I can't turn very much because I need to turn 10 times before I finish the shape. So that's all there is to know for interior angles. They're useful for figuring out missing angles from various polygons. That's Unit 6A2. I would move directly onto Unit 6A3. The homework's going to be combined, and we're going to add in exterior angles of any polygon. Okay, thanks for watching. Bye for now.